Hey everybody. Today we're covering limit laws. Basically, we want to be able to evaluate limits algebraically. We don't always want to have to resort to graphs or to plugging in nearby values when we're evaluating limits. The limit laws are the tool that let us do this. Let's run through the basic ones right away. Limit as x goes to c, f of x plus g of x equals the limit as x goes to c, f of x plus the limit as x goes to c of g of x. Basically, the limit of a sum is the sum of the limits. You can break up that sum in sort of the obvious way. Now, it's important to recognize that this law only holds if the individual limits are both defined, if they're both finite. Limit x goes to c f of x has to be some number, and the limit x goes to c g of x also has to be some number. If either one of those limits don't exist, this limit law doesn't hold, and you have to figure out some other way to do the problem. The other limit laws on this slide are all going to be similar. The limit of a difference is going to be the difference of the limits. The limit of a constant times a function is the constant times the limit of the function. The limit of a product is the product of the limits, and the limit of a quotient is the quotient of the limits, assuming the denominator does not go to 0. If the denominator is going to 0, the right-hand side of that equation doesn't make sense, so we can't use the limit law that way. Let's do a graphical example. Here are y equals f of x and y equals g of x, and I'd like to evaluate the limit as x goes to -1 to f of x minus 5g of x. So we have a limit law that lets us break up this subtraction problem inside the limit as a subtraction of two limits. And then we have another limit law that's going to let us factor out the constant factors. Limit as x goes to -1 of 2f of x will be 2 times the limit as x goes to -1 of f of x. Similarly for the limit of 5g of x. Now I can evaluate these two limits by looking at the graphs. As x gets closer to -1, f of x is getting closer and closer to 3. Don't be fooled by the fact that f of -1 is 1. The limit doesn't care about the value of the function at a point. It only cares about what happens nearby. Similarly, as x goes to -1, g of x is going to -1. So I'm getting 2 times 3 minus 5 times -1, which is a total of 11. Let's do another one using these same graphs. Limit as x goes to 1 from the left of f of x times g of x. Okay, so we've got a one-sided limit here. The limit laws all apply equally well to one-sided limits as to two-sided limits. The limit as x goes to 1 from the left of f times g is going to be the product of the two limits, assuming both of the individual limits exist. Like so. So let's evaluate the two individual limits. As x gets closer and closer to 1 from the left, f of x is getting closer and closer to 1. We're a little bit smaller than x equals 1, and so the graph is going to lie above the x-axis there. It's the left branch of that function. Similarly, as x gets closer and closer to 1 from the left, g of x is getting closer and closer to -1. The function's constant at that point. So overall, I'm getting -1 for my limit. Let's do a couple more limit laws that are, I think, fairly obvious. The limit as x goes to c of a is a, where a is just a constant. So what this is saying is that as x gets closer and closer to c, the constant isn't changing, so the limit is going to be equal to that constant. Secondly, the limit as x goes to c of x is c. Saying this in words, as x gets closer and closer to c, the function x gets closer and closer to c. Pretty obvious. Let's throw in one more that's a tiny bit more complicated. Now's as good a time as any. The limit as x goes to c of f of x to the n is the limit as x goes to c of f of x whole thing to the n. So instead of doing the power first and then the limit, we're doing the limit first and then the power. When n is a positive integer, 2, 3, 4, etc., this is really just limit law 4, which said that the limit of a product was the product of the limits. In fact, it holds for any value of n, as long as both sides of this equation make sense. For instance, we can't take a negative power if we're getting a limit that is going to be 0, because that would put a 0 in the denominator. And we can't have a 1/2 power, for example, if the limit is going to be negative. We can't take a square root of a negative number. If we take the limit laws we have so far and put them together, we get this very, very useful result. If f of x is a polynomial or a rational function, so one polynomial divided by another, and x equals c is in the domain, for example, if it's a rational function, then the limit as x goes to c of f of x is just f of c. So for functions like this, we can evaluate the limits just by plugging in. That's a very powerful result. Here's an example of how it works. Limit as x goes to 2, 3x squared minus 6x plus 1. This is a polynomial. The direct substitution property is going to apply. We just take that value, x equals 2, and plug it in. Simplifying gives us 1 in this case. Pretty easy. Here's an example with a rational function. Limit as x goes to -1 of 4 minus 2x over x plus 9. X equals -1 is in the domain of this function. It does not make the denominator 0. So I can just directly substitute in -1 for x. Simplifying a little bit in this case gives me 3/4. So that works great, but it's important to remember that direct substitution does not work when the denominator of a rational function is going towards 0. Here's an example of what I mean. Limit as x goes to -2, 5x squared minus 10x minus 40 over x squared minus 4. In this case, when I plug in -2, the denominator becomes 4 minus 4, which is 0. The limit laws don't apply. The limit of the quotient won't be the quotient of the limits because the denominator is going to be going to 0. We need to do something else in this case. When the denominator is going to 0 for a rational function, there are two possibilities, basically depending on whether the numerator is going to 0 or not. If the limit of the numerator is a number other than 0, then the overall limit is not going to exist. The graph of the function is going to have a vertical asymptote because the limit's going to a finite number over 0. So it's going to get bigger, the function's going to get bigger and bigger as x gets closer and closer to the value. On the other hand, if the limit of the numerator is 0 as well as the denominator, then the limit is going to be indeterminate. And that just means we have to do more work to figure it out. It could exist and be a finite number. It could be infinite, it could be infinite, it could be negative infinity, or it could just not exist, period. In this case, when we plug in, we get 0 over 0. Both the numerator and denominator are going to 0. So we have to do more work. We've gotten indeterminate. Basically, in this case, that means factoring. We're going to factor the numerator and denominator and hope that something nice happens that will help us to simplify this. The denominator is a difference of squares, x minus 2 times x plus 2. The numerator has a common factor of 5, so I'm pulling that out first. And then I've got a quadratic there on top that's fairly easy to factor. It's x plus 2 times x minus 4. Now I see that I have a factor of x plus 2 on the top and bottom, so I want to cancel those out. By the way, notice because we have a limit going towards -2, x is never actually equal to -2, so x plus 2 is never actually equal to 0 inside that limit, so this cancellation really does make sense. I'm left with 5 times x minus 4 over x minus 2. Now, x equals -2 is in the domain of the function I have inside the limit. Now the limit laws do apply, and I can just use direct substitution. I plug in -2, I get 5 times -6 over -2 minus 2, which is -30 over -4, which just simplifies to 7.5. Let's wrap up by looking at a graph of this function. Here it is. It has a hole at x equals -2, reflecting the fact that that value is not in the domain. In this case, Even though the denominator of the rational function is 0, we do not have a vertical asymptote.